Within the vast expanse of the solar system lies a quiet paradox. There is a planet that humanity has never reached and may never reach, yet it silently determines the fate of another world, ensuring that it remains forever smaller than its true potential. This restraint does not come from violent collisions or sudden catastrophes. It comes from position, from immense mass, and from a presence so persistent that it cannot be escaped. That planet is Jupiter, the gas giant with its deep, endless layers of cloud, a realm where absolute silence reigns and where all human understanding must be built from a careful distance. And it is precisely this distance that reflects the destiny of Mars, a cold, red world closer to the Sun, marked by the traces of what might have been, but never came to pass. Between these two opposing worlds lies not an empty void, but the asteroid belt, a wordless boundary, a structured stillness suspended between two very different fates. In this journey, we will not move closer to examine surfaces or details. Instead, we will remain far enough away, quiet enough to perceive the slow yet powerful connection linking Jupiter, Mars, and the elusive space that lies between them. In the outer reaches of the solar system, one planet quietly outweighs nearly everything else beyond the inner worlds. Jupiter carries almost all the mass of the region it inhabits. Its gravity is not sudden or aggressive. It does not announce itself. It simply exists, steadily shaping the space around it over immense spans of time. Closer to the Sun, far inside that realm of influence, lies a very different world. Mars is small, cold, and still. It never became a second Earth. Its atmosphere thinned, its surface cooled. Its internal activity slowed long ago, not because something dramatic went wrong, but because certain conditions quietly failed to persist. These two planets are not neighbors. They do not orbit side by side. From a human perspective, they seem unrelated, separated by vast distances and very different environments. And yet, when scientists look at the solar system as a whole, their histories do not unfold independently. Jupiter represents abundance. It formed quickly and efficiently, gathering enormous amounts of material before the young solar system settled into long-term stability. Mars represents limitation. It formed in a region where growth was possible, but fragile, where small differences in environment could lead to lasting consequences. This contrast is not accidental. Space rarely gives us simple answers. From Earth, we are used to thinking in terms of surfaces, oceans, mountains, atmospheres. But planetary destiny is decided long before any surface becomes familiar. It begins with where a planet forms, when it forms, and what surrounds it during those earliest moments. Jupiter's immense mass creates a gravitational presence that extends far beyond its visible size. Even worlds that never come close can feel its influence indirectly, not as a force you could experience in a single moment, but as a slow shaping of probabilities. Over time, that quiet pressure matters more than any single collision or event. Mars formed in a more delicate balance. It had enough material to become a planet, but not enough to continue growing. Enough heat for early geological activity, but not enough to sustain it indefinitely. Enough gravity to hold an atmosphere for a while, but not forever. When scientists study Mars, they do not see failure, they see constraint. Numbers whisper more than they speak. What makes this relationship difficult to notice is that Jupiter and Mars never interact directly in any obvious way. There is no visible exchange. No dramatic encounter, no moment you could point to and say, this is where everything changed. Instead, the connection between them is written into the structure of the solar system itself, into the way mass is distributed, into the way space between worlds behaves over long periods of time. Silence is also a kind of data. For humans, there is something quietly familiar in this pattern. Growth is not determined by effort alone. It is shaped by surroundings, by timing, and by forces that rarely announce themselves. Some environments allow expansion to continue. Others limit it early, not through conflict but through circumstance. From a distance, Jupiter appears calm and unchanging. Mars appears inactive and still. But beneath that stillness lies a shared history, one that does not unfold on the surfaces of planets, but in the space between them. And that space, often overlooked, will turn out to matter far more than it seems. Jupiter does not need to move quickly to matter. It does not need to collide, erupt, or announce itself through dramatic change. Its influence comes from something far quieter. Mass held steadily in place over very long periods of time. In the solar system, Jupiter is not defined by what it does, but by what it is, a vast concentration of material gathered early, remaining largely where it formed. Its gravity does not surge or fade. It persists, and persistence in space is often more powerful than action. For humans, this can be difficult to intuit. We are used to cause and effect happening close together in time. A push leads to motion, an impact leads to damage. But gravity does not work on human timescales. Jupiter's pull operates patiently, shaping paths and limits not in moments, but across millions and billions of years. Space rarely gives us simple answers. Jupiter's gravitational field extends far beyond the planet itself, not as a sharp boundary, but as a gradual presence that blends into the surrounding space. Objects do not need to come near Jupiter to be affected by it. They only need to exist within its broader gravitational environment. Over time, that environment guides motion, restricts accumulation, and defines what remains stable and what does not. Importantly, Jupiter does this without changing much. Its orbit is remarkably steady. Its position relative to the rest of the solar system shifts only slowly. There is no constant upheaval, no ongoing chaos. From a distance, Jupiter appears calm, almost inert. Yet that apparent stillness is exactly what makes its influence so profound. Numbers whisper more than they speak. When scientists describe Jupiter's role, they often rely on mass ratios and gravitational parameters. But behind those numbers lies a simple idea. A very large object remaining in place for a very long time reshapes the environment around it whether it intends to or not. Jupiter does not choose to influence, it cannot stop influencing. This kind of influence is easy to overlook because it lacks drama. There is no single moment when Jupiter changes everything. Instead, there is a slow narrowing of possibilities. Certain paths become unlikely. Certain outcomes become impossible. Other outcomes quietly become inevitable. For people, there is something deeply familiar in this pattern. We recognize how environments shape lives without direct intervention. A stable background can encourage growth or quietly limit it without ever drawing attention to itself. Jupiter operates in much the same way. Silence is also a kind of data. One of the most striking things about Jupiter is how little it needs to change to remain dominant. While smaller worlds cool, fracture, and evolve rapidly, Jupiter remains largely consistent. Its internal dynamics are complex, but its external influence is steady. That steadiness matters more than intensity. In the early solar system, when material was still moving, colliding, and attempting to gather into worlds, Jupiter's presence acted like a constant condition. Not a barrier, not a wall, but a background rule. Over time, that rule shaped how nearby regions behaved, even if no single object could point to Jupiter and say it was directly affected. Humans often look for agents and events. We ask what happened and when. Jupiter answers a different question. It shows what happens when something simply remains, unchanged enough for long enough. From Earth, Jupiter appears distant and unreachable. We observe it through telescopes and instruments, translating light and motion into understanding. That distance reinforces the idea that Jupiter is separate from the inner worlds, disconnected from everyday planetary stories. But distance in space does not mean irrelevance. What Jupiter demonstrates is that influence does not require proximity. It requires presence. And presence, sustained over time, becomes structure. As we continue, the importance of this quiet, persistent influence will become clearer. Not through sudden revelations, but through the slow unfolding of relationships shaped by gravity and time. In the solar system, the most powerful forces are often the ones that do not need to move at all. Mars formed at the outer edge of the rocky planet region, a place where conditions begin to change quietly but decisively. It was close enough to the Sun to belong to the inner worlds, yet far enough away that growth was never guaranteed. This position mattered more than it first appears. Mars is small, not by accident, but by circumstance. Its mass is modest, its gravity is limited. From early on, it lacked the amount of material needed to continue growing. But this was not because Mars failed to gather what it needed. It formed in a region where there simply was not much left to gather. From Earth, it is tempting to see Mars as a world that almost became something else. Dry riverbeds, ancient deltas, and mineral traces suggest a past that was more active, more dynamic. But these signs do not point to misfortune. They point to constraint. Mars did what it could with what was available to it. Space rarely gives us simple answers. In the early solar system, the region where Mars formed was already becoming sparse. Material was unevenly distributed. Some areas accumulated mass efficiently, others did not. Mars emerged in one of those quieter zones where growth slowed before it could truly take hold. This does not make Mars weak. It makes Mars precise. Its size tells a story about balance and limits. Enough material to form a planet, not enough to sustain long-term internal heat. Enough gravity to hold an atmosphere for a time, not enough to keep it indefinitely. Numbers whisper more than they speak. When scientists compare Mars to Earth, the differences are often framed as losses. A thinner atmosphere, a cooler interior, a quieter surface. But these are outcomes, not causes. The cause lies deeper in the environment that shaped Mars from the beginning. Planetary formation is not a competition where all worlds start equal. It is a process governed by gradients. Temperature changes with distance, material density shifts, gravitational influences overlap. Mars formed where these gradients intersected in a particularly delicate way. For humans, this idea is intuitive in another context. Outcomes are rarely determined by effort alone. They are shaped by surroundings, by timing, and by access to resources that are not evenly distributed. Mars reflects this principle on a planetary scale. Silence is also a kind of data. Mars shows us what happens when a world grows just enough, then stops. It retains a record of early conditions that larger planets overwrite through continued activity. Its surface preserves a memory of the solar system's youth, not because it is frozen in time, but because it never had the means to erase that memory. Importantly, Mars did not evolve in isolation. Its position placed it in a transitional zone, not fully protected by proximity to the Sun, not fully removed into the outer reaches. It existed in a space where influences overlapped, even if they were not immediately visible. This makes Mars a sensitive indicator, a planet that responds strongly to subtle changes in its environment. Small shifts in available material or in surrounding gravitational conditions had lasting effects. Mars records those effects quietly in its size, its structure, and its long-term evolution. From Earth, Mars often feels close. It is the most familiar of the other planets. We imagine standing on its surface, looking back at our own world. But familiarity can be misleading. Mars is not a failed Earth. It is a planet shaped by a different set of background conditions. As we continue, it will become clear that Mars's story cannot be told by looking at Mars alone. Its size, its limits, and its early history point outward, toward the space around it, toward influences that did not arrive suddenly, but were present from the beginning. In planetary history, what a world becomes is often decided not by chance, but by where it stands when everything else is still forming. Between Mars and Jupiter, there is a region that is often misunderstood. From a distance, it appears empty, a wide gap separating a small rocky planet from a massive gas giant. But this space is not a void, and it was never meant to be one. It is also not a planet. What exists there is something quieter, more subtle. A broad zone filled with countless small bodies, each following its own path around the Sun. Together, they form what we call the asteroid belt. Not a world, not a failure, but a region that stopped changing before it could become something else. This space once held far more than it does now. In the early solar system, material was spread across wide distances. Dust, ice, and rock moved slowly within a rotating disk, gathering where conditions allowed. The region between Mars and Jupiter was not poor or empty in those early moments. By all reasonable measures, it contained enough material to build something much larger than what remains today. And yet, it never did. Space rarely gives us simple answers. When we imagine planetary formation, we often picture a straightforward process. Material gathers, objects collide gently, growth continues until a planet emerges. But this picture is incomplete. Growth does not happen everywhere equally. Some regions advance quickly, others slow down, some stop altogether without any obvious sign that something went wrong. The space between Mars and Jupiter is one of those regions. What remains today are fragments, not because something was destroyed in a single event, but because growth never fully completed. The process paused, the system moved on, and what was left behind became a kind of record, preserved not by stillness, but by incompletion. For humans, this idea can feel unfamiliar. We tend to think of unfinished things as broken or interrupted. In space, unfinished does not imply failure, it often implies balance. A state where opposing influences prevent further change without erasing what already exists. Numbers whisper more than they speak. When scientists measure the total mass of the asteroid belt today, the number is surprisingly small. Much smaller than the mass of Earth, smaller even than the Moon. That quiet fact carries more meaning than it seems to at first glance. It tells us that most of the original material is no longer there, not gathered into a planet, not visible in one place, simply gone, redistributed, or never allowed to settle. And yet the region itself remains, stable, structured, persistent. The objects within this space follow predictable paths. Their orbits are not random. They are shaped by long-term conditions that favor order over chaos. From afar, the asteroid belt appears calm, almost static. But that calm hides a long history of adjustment, where motion continues but growth does not. Silence is also a kind of data. The most important feature of this region may be what it lacks. No dominant body, no single object large enough to take control. Instead, there is a shared balance where many small objects coexist without merging into something larger. This balance is not accidental. It reflects the environment in which the region exists. Positioned between a small inner planet and a massive outer one, the space between them occupies a sensitive location. Close enough to the inner solar system to matter. Close enough to the outer solar system to be influenced, yet fully belonging to neither. For people, this kind of in-between space feels familiar. Not every environment pushes toward completion. Some hold things in place, allowing them to persist without resolving into a final form. The asteroid belt is such a place, a region defined not by what it became, but by what it did not. At this stage of our journey, there is no need to explain why this region stopped short of becoming a planet. The reasons are complex and they unfold slowly. What matters now is the recognition of the paradox itself. Between Mars and Jupiter lies a space that once promised more, yet remains exactly as it is. Not empty, not complete. Quietly suspended between two very different worlds. And sometimes, in the structure of a system, what remains unfinished tells us more than what reaches an end. For a long time, the space between Mars and Jupiter carried a simple explanation. It was thought to be the remains of a planet that once existed and was later destroyed. A world torn apart by some ancient catastrophe, leaving behind fragments scattered along a shared path around the sun. It was an idea that felt intuitive, even dramatic, and for many years it lingered in textbooks and public imagination. But over time, that story quietly faded. What replaced it was not a new mystery, but a clearer understanding. One built slowly through careful observation and comparison. The more scientists studied the region we now call the asteroid belt, the more one conclusion became difficult to avoid. There was no missing planet, no shattered world, no evidence of a violent end. Space rarely gives us simple answers. If a planet had once formed there and later been destroyed, we would expect certain signs. A total mass comparable to a full-sized planet, fragments carrying consistent chemical fingerprints, evidence of forces capable of tearing apart a solid world. None of these appear. Instead, the numbers tell a quieter story. The total mass of the asteroid belt today is surprisingly small. Far smaller than Earth, smaller even than the Moon. This alone rules out the idea of a former planet. Too much material is missing. Not broken into pieces, but absent altogether. Numbers whisper more than they speak. There is also the question of mechanism. Physics does not offer an easy way to destroy a fully formed rocky planet and disperse its remains so evenly without leaving clear traces. The energies involved would be extreme, and the aftermath unmistakable. Yet what we see in the asteroid belt is not chaos, but order. Stable orbits, predictable motion, a region shaped by long-term balance, not sudden violence. As understanding improved, scientists began to see the asteroid belt not as debris, but as something incomplete. A population of objects that began the process of planetary growth but never finished it. Not because something interrupted them violently, but because conditions slowly became unfavorable. This shift in perspective matters. To say that a planet was never born is very different from saying it was destroyed. One implies failure, the other implies limits. The asteroid belt reflects a region where growth started, progressed to a certain point, and then quietly stopped. For humans, this idea can feel unfamiliar. We are drawn to stories with clear beginnings and endings, creation and destruction. In space, many outcomes exist in between. Processes pause. Systems stabilize. What remains is not broken, simply unresolved. Silence is also a kind of data. The objects in the asteroid belt show signs of early formation. They are not raw dust. Many are differentiated. Some experienced heating. Others contain ancient materials that have barely changed since the solar system's earliest days. These clues tell us that growth once occurred here, even if it never reached completion. Importantly, this unfinished state is stable. Over billions of years, the region has persisted without assembling into a dominant body. That stability would not exist if it were the aftermath of destruction. Debris fields disperse, shocked systems relax. The asteroid belt, by contrast, maintains its structure. This tells us something fundamental about how planets form. Completion is not guaranteed. Being in the right place matters. Being surrounded by the right conditions matters even more. The asteroid belt was not unlucky. It was simply positioned in an environment where growth could not continue. Seen this way, the region becomes less of a mystery and more of a record. A snapshot of planetary formation paused mid-process. It shows us what happens when accumulation slows, when mass remains distributed rather than concentrated. For people, this carries a quiet familiarity. Not everything unfinished is the result of damage. Sometimes the environment changes before a process can reach its conclusion. What remains is not a ruin, but a trace of what once seemed possible. The asteroid belt stands as evidence of that truth. Not the remains of a lost world, but the outline of one that never came fully into being. And in the history of the solar system, what never formed can be just as revealing as what did. To understand what did not happen, we need to return to a time when everything still could have. In the earliest chapters of the solar system's history, the space around the young sun was not clean or empty. It was filled with motion. Fine dust drifted through warm gas. Tiny grains collided gently and, under the right conditions, stuck together. Over time, those grains became larger particles. Those particles became clumps, and some of those clumps grew into bodies large enough to shape their surroundings. This was not a rare process. It was happening across wide regions at once. In the zone that would later become the asteroid belt, the situation was no different at first. Material was present in abundance. Models of the early solar system suggest that this region once held enough solid matter to build several Earth-sized planets. There was no initial shortage, no obvious limitation, no sign that growth was doomed from the beginning. Dust became pebbles. Pebbles gathered into larger aggregates. Gravity began to matter. As collections of material grew, they crossed important thresholds. Once bodies reached a certain size, gravity helped them pull in nearby matter more efficiently. These early building blocks, often called planetesimals, ranged from a few kilometers to hundreds of kilometers across. They were not planets, but they were no longer fragile. From a human perspective, this phase feels productive and optimistic. Many paths were still open. Many outcomes were possible. Growth was underway, and nothing yet suggested it would stop. Space rarely gives us simple answers. The key detail is that these early processes do not depend on intention or direction. They follow local conditions: density, temperature, relative motion. When those factors align, growth proceeds. When they drift apart, growth slows. At this stage, the region between Mars and Jupiter was not failing, it was participating. Over the first 1 to 2 million years, accumulation continued. Material circulated. Collisions occurred, mostly gentle enough to build rather than break. The environment supported assembly. There was no single moment when the region was marked as different from others closer to the Sun. Numbers whisper more than they speak. When scientists reconstruct this period using simulations and physical models, the results are consistent. The early belt region was not starved. It was not dynamically chaotic at first. It was capable of producing large bodies, and it did. Some of those bodies still exist today as relics of that era. What makes this important is not just what formed, but what did not prevent formation. There was no early disruption, no sweeping instability, no immediate interference that shut the process down. For a time, the system behaved as expected. Silence is also a kind of data. The absence of early failure tells us something crucial. Whatever changed later was not built into the region from the start. The pause in growth was not inevitable. It emerged gradually as the broader environment of the solar system evolved. For humans, this idea is intuitive in hindsight. Many systems function well at first. They follow familiar patterns. Only later do external influences begin to matter. Conditions shift, thresholds are crossed. Processes that once worked smoothly begin to stall. In the early solar system, timing was everything. While the inner regions continued to assemble larger worlds, the region farther out remained sensitive to changes happening elsewhere. It did not collapse, it did not break apart, it simply began to lose its momentum. From our vantage point, billions of years later, it is easy to assume that the present outcome was always destined. But the evidence suggests otherwise. The early conditions allowed for much more than what we see today. The system did not start with limits clearly drawn. Growth slowed not because the building blocks disappeared overnight, but because the environment around them changed. Relative motions increased. Encounters became less gentle. The balance that once favored accumulation shifted toward a different state. At this stage of the story, it is enough to recognize this turning point without explaining it fully. The important fact is that the region once had what it needed. Material was present. Processes were active. There was a clear signal of failure. Everything that came after was a response to changing conditions, not a correction of an early mistake. In complex systems, beginnings are often generous. It is the gradual evolution of the environment that decides what can continue and what must quietly stop. As the solar system continued to mature, one change mattered more than any other. Jupiter reached a critical mass. This did not happen suddenly, and it did not announce itself with a single dramatic moment. Jupiter grew steadily, gathering gas and material until its gravity became a dominant feature of the system. From that point on, space around it began to behave differently. Not violently, not chaotically, but subtly and persistently. Gravity does not need contact to matter. Once Jupiter became massive enough, its influence extended far beyond its immediate neighborhood. The paths of nearby objects did not break apart. They began to drift. Orbits that were once nearly circular grew slightly elongated. Inclinations increased. Motions that had been calm became just a little less predictable. This was enough. In regions closer to Jupiter, and even well inside its orbit, the effect was not direct force but long-term pressure. Objects continued to circle the Sun, but their rhythms were no longer perfectly aligned. Over time, small changes accumulated. The system moved away from balance, not through disruption, but through gradual misalignment. Space rarely gives us simple answers. In the region that would become the asteroid belt, these changes were especially important. For a time, collisions there had favored growth. Bodies met at low relative speeds, allowing them to merge. But as Jupiter's gravitational reach strengthened, relative velocities increased. Impacts became sharper. Encounters that once built larger bodies began to chip them away instead. Construction quietly gave way to erosion. Numbers whisper more than they speak. There is a threshold in planetary formation that is easy to overlook. Growth depends not just on how much material is present, but on how gently that material can come together. Once collision speeds exceed a certain range, impacts no longer lead to accumulation. They lead to fragmentation. Jupiter did not need to remove material from the region to change its fate. It only needed to change how that material interacted. This shift marked a turning point. The asteroid belt did not collapse. It did not scatter instantly. It entered a new phase, one where growth was no longer favored. The process that had once allowed planetesimals to combine slowed, then stalled. Silence is also a kind of data. Farther inward, the effects were less obvious, but no less important. Mars formed in a region that was already delicate. Its growth depended on a steady supply of material and stable conditions. As Jupiter's influence spread, the inner edge of the outer solar system became a place of subtle disruption. Material that might have drifted inward was redirected. Paths became less efficient. Accumulation slowed. Mars did not lose what it had already gained, but it stopped gaining more. This connection is easy to miss because there is no clear line between cause and effect. Jupiter never approached Mars. There was no close encounter, no dramatic exchange. Yet the timing matters. Mars was still forming while Jupiter was becoming dominant. That overlap shaped the outcome. For humans, this kind of influence feels familiar. Environments change without confrontation. A background condition shifts, and long-term plans quietly become impossible. Nothing breaks, nothing collapses. Progress simply stops. The asteroid belt sits between these two worlds as a record of that transition. It absorbed much of the change directly, shifting from a region of growth to one of fragmentation. Mars felt the effect indirectly, as reduced access to material limited its final size. Jupiter remained largely unchanged, its mass steady, its role complete. Silence is also a kind of data. What makes this chapter pivotal is that it links three regions into a single story. Jupiter's growth altered the behavior of space around it. That altered behavior changed how material moved and interacted. And those changes shaped what the inner planets could become. This was not a chain reaction. It was a gradient, a slow spread of influence that did not need forceful intervention. Jupiter did not act against the inner worlds. It simply existed, and that was enough. From Earth, we often look for dramatic agents, but the solar system reminds us that the most important influences are often environmental. They shape outcomes by defining limits rather than delivering blows. As we move forward, the consequences of this quiet shift will become clearer. The asteroid belt will emerge not as a remnant of destruction, but as a region transformed by changing conditions. Mars will stand as a world shaped as much by what could not reach it as by what did, and Jupiter will remain what it has always been in this story. Not a force that strikes, but a presence that endures, quietly redefining what is possible for everything around it. There was no single moment when planetary formation stopped in the region between Mars and Jupiter. No explosion, no sudden clearing of space. No event dramatic enough to mark an ending. Instead, the process simply became less effective. In the early solar system, growth depended on accumulation. Small bodies met at gentle speeds, merged and slowly became larger. Over time, this created a natural pathway from dust to pebbles, from pebbles to planetesimals, and from planetesimals toward planets. For a while, this pathway remained open. Then quietly it did not. As gravitational conditions shifted, relative velocities increased. Objects still collided, but the nature of those collisions changed. Encounters that once led to growth now resulted in fragmentation. Pieces broke away instead of sticking together. The building process did not reverse, but it stalled. Space rarely gives us simple answers. In the region we now call the asteroid belt, this transition was gradual. Nothing collapsed, nothing was erased. The population of small bodies remained, but their interactions no longer favored the formation of a dominant world. Accumulation slowed until it became statistically unlikely. Growth did not fail catastrophically. It simply stopped being efficient. This distinction matters. When we think about endings, we often imagine disruption. In planetary systems, many endings are defined by thresholds. Once certain conditions are crossed, a process can no longer continue, even if all the ingredients remain present. The asteroid belt crossed such a threshold. Numbers whisper more than they speak. Simulations of this period show that only a modest increase in collision speeds is needed to change outcomes entirely. There is a narrow window where growth works. Outside that window, impacts grind material down rather than build it up. Jupiter did not need to remove mass from the region to close that window. Its growing gravitational influence was enough to alter the background conditions. The result was a quiet freeze in development. The asteroid belt did not become a planet because it no longer could. Not because something destroyed it, but because the environment no longer supported continued assembly. Over time, collisions continued, but they led to smaller fragments instead of larger bodies. A cascade of breakage replaced a ladder of growth. Silence is also a kind of data. Farther inward, the same change carried consequences for Mars. Mars was still forming when these conditions shifted. Its growth depended on steady access to material and a relatively calm environment. As the region beyond it became less efficient at delivering mass inward, Mars reached its natural limit sooner than Earth did. Mars did not lose material, it simply stopped gaining it. This is why Mars appears incomplete when compared to Earth. Its size reflects a process that ended early, not one that failed outright. The planet achieved what it could under the conditions available to it, then stabilized. For humans, this pattern feels familiar. Many systems slow not because they break, but because the environment around them changes. Effort continues, but results diminish. Eventually, progress becomes negligible, even though activity remains. Silence is also a kind of data. From a distance, the solar system after this transition looked calm. Orbits settled into stable patterns. The major planets followed predictable paths. Nothing obvious marked the end of formation in the asteroid belt or the final sizing of Mars. But beneath that calm, a fundamental shift had already occurred. The region between Mars and Jupiter entered a new phase, one defined not by creation, but by persistence. What existed would remain. What had not yet formed would never fully do so. This is why there is no single story of destruction to tell here. The system did not need one. The outcome was shaped by gradual changes accumulating over time, by small differences that, together, closed the door on further growth. As observers, we are drawn to events, but the history of the solar system reminds us that many of the most important changes are processes, not moments. They unfold quietly, without announcement, and only reveal themselves when we look back. The asteroid belt remained a belt. Mars remained small. Jupiter remained massive. And the system moved on. In the long arc of planetary history, endings do not always arrive with impact. Sometimes, they arrive as a steady narrowing of possibility, until what once could happen simply no longer can. For most of this story, Jupiter has appeared as a steady presence. Massive, persistent, anchored in place. But there was a time, very early in the solar system's history, when Jupiter did not remain where it is today. This movement was not sudden, and it was not chaotic. It unfolded slowly, guided by the same gravitational rules that govern everything else in space. Yet its consequences were profound. This idea is known as the grand tack, a model that describes a brief but important migration of Jupiter during the system's formative years. Jupiter formed farther from the Sun than it is now. As it grew and interacted with the surrounding disk of gas, its orbit began to change. Gradually, Jupiter moved inward, closer to the Sun. Not rushing, not disrupting everything in its path. Simply drifting, guided by long-term gravitational exchanges. Space rarely gives us simple answers. As Jupiter moved inward, it passed through regions that were still actively forming. Material that had once followed relatively stable paths was disturbed, not destroyed, but redirected. Orbits shifted. Some objects were pushed inward. Others were sent outward. Many were removed from the region entirely. This was the first restructuring. Later, as Saturn grew and entered a gravitational resonance with Jupiter, the direction of movement changed. The two massive planets became linked in their motion. Together, they reversed course. Jupiter began to move outward again, retreating toward the position it occupies today. This outward journey was the second restructuring. Each pass through the region between Mars and Jupiter altered its contents. Material that had survived earlier phases of formation was scattered. Some fragments were incorporated into inner planets. Others were ejected from the solar system altogether. Very little remained where it started. Numbers whisper more than they speak. When scientists estimate how much material was lost during this process, the result is striking. Only a small fraction of the original mass stayed behind. What we see today in the asteroid belt represents a tiny remnant of what once existed. Not because the region was empty to begin with, but because repeated reshaping left very little untouched. Importantly, this was not destruction in the dramatic sense. Jupiter did not sweep the region clean in a single motion. The process unfolded over time, with material responding differently depending on its location and timing. Some objects were caught in stable configurations, most were not. Silence is also a kind of data. From a human perspective, it is tempting to imagine migration as violent. But the grand tack was governed by slow forces acting over long periods, gas interactions, orbital resonances, gradual exchanges of angular momentum. Nothing exploded. Nothing shattered instantaneously. The system simply rearranged itself. Mars felt the effects as well. During Jupiter's inward movement, material that might have contributed to Mars's growth was removed or redirected. When Jupiter moved outward again, the environment Mars occupied was already depleted. This helps explain why Mars remained small, even though early conditions had once allowed for more growth. The asteroid belt, positioned between these two worlds, was reshaped most directly. Its original population was reduced, scattered, and mixed. What survived was not a pristine remnant, but a collection of objects that happened to find stability after repeated disturbances. For humans, this kind of history feels familiar in another way. Systems rarely change all at once. They go through phases of adjustment. Each adjustment leaves fewer options than before. Over time, what remains is not what was planned, but what could adapt. The grand tack does not claim to explain every detail of the solar system. It is one model among several. But it offers a coherent way to understand how a region once rich in material could end up so sparse, and how Jupiter's influence extended beyond simple gravity into the architecture of the system itself. What matters most is not the exact path Jupiter took, but the fact that it did not remain fixed during a critical period. Its movement, slow and guided, reshaped the distribution of material long before the solar system reached stability. By the time Jupiter settled into its present orbit, Much of the early chaos had already passed. The inner planets had taken shape. The asteroid belt had been reduced to a fraction of its former self. Mars had reached the limits of its growth. What remained was not the original design, but the outcome of repeated reorganization. And in the quiet structure we observe today, the solar system still carries the memory of that ancient movement, reminding us that even the most stable presences were once in motion. What we see today in the region between Mars and Jupiter is not a single story preserved in place. It is a collection. The asteroid belt is often spoken of as though it were one thing, formed once and left unchanged. But when scientists look closely, they see something very different. The belt is not uniform, it is not original. It is a gathering of objects with different histories, brought together by circumstance rather than shared origin. Some of the bodies in the region are dry and rocky. They resemble the materials found closer to the Sun, shaped by higher temperatures and early heating. These objects tend to occupy the inner part of the belt, where sunlight is stronger and volatile materials were harder to keep. Farther out, the composition changes. Objects there are darker, richer in carbon, and more likely to contain water-bearing minerals and complex compounds. These materials resemble what we would expect to find much farther from the Sun, in colder regions where ice and organic compounds could survive. This contrast is not subtle. Numbers whisper more than they speak. When scientists sort asteroid populations by composition, the pattern is clear. The belt is layered not by design, but by history. Dry materials dominate the inner regions. Carbon-rich bodies are more common farther out. The transition is gradual, not sharp, reflecting a process shaped over time rather than a single event. This tells us something important. The asteroid belt did not form as a closed system. It did not inherit a single set of conditions and remain isolated. Instead, it was reshaped repeatedly. Objects were added, removed, and redistributed. What remains today is a mixture of survivors. Space rarely gives us simple answers. Some of the objects now in the belt likely formed closer to the Sun and were pushed outward. Others may have originated farther away and were drawn inward. Their current positions do not reflect their birthplaces. They reflect where they eventually found stability. For humans, this idea is easy to relate to. Collections rarely form from a single source. Museums, libraries, even memories are built from many paths converging. The asteroid belt is similar. It is not an archive of one moment, but a record assembled over time. Silence is also a kind of data. The lack of uniformity itself is a clue. If the belt were the remains of a single destroyed planet, we would expect consistency, similar compositions, shared chemical signatures. Instead, we see diversity. Objects that tell different stories, shaped by different environments, yet now sharing the same broad region of space. This diversity makes the asteroid belt scientifically valuable. Each object carries information about the conditions under which it formed. Some preserve materials altered by early heating. Others contain compounds that have changed little since the solar system's youth. Together they offer a wider view than any single planet could. From a distance, the belt looks quiet and orderly. Objects follow predictable orbits. The region appears stable. But that stability is the result of selection. Only certain paths remain viable over long periods. Only certain objects persist. What we see today is not representative of everything that was once there, but of what could remain. For Mars and the inner planets, this collection mattered. Carbon-rich objects likely contributed water and volatile materials to worlds closer to the Sun. Dry, rocky bodies reflect conditions that dominated nearer regions. The belt became a kind of intermediary, not because it was designed to be one, but because it ended up in that role. The asteroid belt, then, is not a pristine remnant. It is not a failed planet frozen in time. It is a curated outcome of countless interactions, migrations, and losses. Its current structure reflects survival rather than origin. For people, there is a quiet lesson here. What surrounds us is often not what began together. It is what endured together. Systems accumulate not only what they create, but what they are able to keep. As we move forward, this view will matter. Understanding the belt as a collection helps explain why it looks the way it does today and why its influence reaches beyond its modest size. In the solar system, as in many complex systems, what remains is rarely pure. It is assembled, layered, and shaped by time. Within the wide span between Mars and Jupiter, two bodies stand out. Not because they are large, and not because they dominate their surroundings, but because they quietly preserve different chapters of the same history. Ceres and Vesta share the same general neighborhood, yet they tell very different stories. Together, they act as witnesses to a time when this region was still deciding what it would become. Ceres is the larger of the two, round enough for gravity to have shaped it into a sphere. That shape matters. It tells us that Ceres once held enough internal heat, enough mass to behave like a world rather than a fragment. What makes Ceres especially interesting, however, is not its size, but its composition. Ceres contains water. Not just traces, but significant amounts locked into minerals, salts, and possibly deep layers beneath its surface. Evidence suggests that Ceres may even have hosted a subsurface ocean at some point in its history. For a body located between Mars and Jupiter, this is remarkable. Ceres looks less like a typical asteroid, and more like something that formed farther from the Sun, in a colder environment where water and volatile materials could survive. Its presence here suggests movement, a journey, a history that did not begin exactly where it now resides. Space rarely gives us simple answers. Vesta tells a different story. Smaller than Ceres and irregular in shape, Vesta shows clear signs of differentiation. It once had a molten interior, a dense core, a rocky mantle, a basaltic crust. These are features we associate with planets, not debris. Vesta did not remain small because it lacked ambition. It remained small because its growth stopped early. It formed quickly, heated up, and began the process of becoming a planet. Then that process was cut short. Not violently, but decisively. Numbers whisper more than they speak. Meteorites found on Earth have been traced back to Vesta. Their chemistry matches its surface, providing a direct physical link between this small body and our planet. Through these samples, we know that Vesta's internal evolution was real, not theoretical. It was once on a path toward becoming something larger, and then it was not. What makes these two bodies so valuable is not their individual features, but their contrast. Ceres appears rich in water and altered by chemistry that requires time and relative stability. Vesta appears dry, dense, and shaped by early heat. One looks outward toward colder regions of the solar system. The other looks inward toward the rocky planets. Silence is also a kind of data. Together, Ceres and Vesta reveal that the region between Mars and Jupiter was never uniform. It hosted multiple pathways of development at the same time. Some bodies accumulated water, others differentiated internally. Some grew quickly, others evolved slowly. Both bodies survived, not because they were dominant, but because they found stable configurations early enough. They avoided further growth, avoided destruction, and remained as they were while the rest of the system moved on. For humans, there is something comforting in this. Not every story ends with completion. Some end with preservation. Ceres and Vesta were not meant to become planets in the final solar system. Instead, they became records. They show us what was possible in that region and what was interrupted. They carry evidence of both abundance and limitation. And they do so without drama, simply by existing. Ceres reminds us that water was present in places we do not always expect. Vesta reminds us that planetary beginnings can be halted without being erased. Together, they occupy the space between two much larger worlds, quietly holding information that those larger worlds no longer retain. Mars moved on. Jupiter dominated. The smaller bodies remained. As witnesses, they do not tell us what should have happened. They show us what did happen, in fragments and contrasts that require patience to interpret. And sometimes, in the story of a system as large as the solar system, the smallest survivors are the ones that remember the most. When we return to Mars, it becomes clear that its small size is not a mystery waiting for a dramatic explanation. It is a record of timing and environment. Mars did not become small because something went wrong. It became small because something quietly ended early. From the beginning, Mars formed near the outer edge of the rocky planet region. That position placed it close to zones where material was already becoming scarce. As the solar system evolved, the supply of solid matter available to Mars diminished. Not abruptly, but steadily. Growth slowed, then stopped. Mars did not lose a large amount of mass, it simply stopped receiving more. This distinction is important. Loss implies damage. Mars shows no sign of catastrophic stripping during its formation. Instead, its size reflects a planet that reached equilibrium sooner than Earth did. The environment around it changed, and the process of accumulation could no longer continue. Space rarely gives us simple answers. One of the key factors in this change was distance. Jupiter never approached Mars. There was no close encounter, no gravitational tug-of-war. Yet Jupiter's influence extended across the solar system, reshaping how material moved long before Mars finished forming. As Jupiter grew and stabilized, it altered the flow of debris and planet-building material. Paths that once allowed matter to drift inward became less effective. Some material was redirected. Some was scattered outward. Over time, less reached the region where Mars was still trying to grow. Numbers whisper more than they speak. When scientists model the early solar system, they see this effect clearly. Even small changes in how material circulates can have large consequences over millions of years. Mars did not need a dramatic disruption to end up smaller than Earth. It only needed the supply lines to weaken while growth was still underway. This explains why Mars looks incomplete when compared to Earth. Its core cooled faster. Its gravity was never strong enough to hold a thick atmosphere for long. Volcanic activity faded earlier. These are not independent failures. They are all downstream effects of limited growth. Silence is also a kind of data. Mars preserves evidence of its early potential. Ancient river channels and mineral deposits show that liquid water once existed on its surface. For a time, Mars had enough heat, enough atmosphere, and enough stability to support more active conditions. Then those conditions gradually disappeared. The reason lies not only on Mars itself, but in the environment beyond it. As material in the region between Mars and Jupiter stopped accumulating and began fragmenting instead, Mars lost access to resources that might have extended its growth. The planet reached its natural limit sooner than Earth did. For humans, this pattern is familiar. Outcomes are often shaped by factors beyond direct control. Growth depends not just on internal effort, but on access, timing, and background conditions that may change without warning. Mars reflects this principle on a planetary scale. Importantly, Mars is not a failed Earth. It is a complete Mars. Its size, structure, and history are consistent with the environment in which it formed. Judged on its own terms, it did exactly what physics allowed it to do. What makes Mars especially valuable to science is this clarity. Larger planets erase their early history through continued activity. Mars, by stopping early, preserved it. Its surface and interior retain information about conditions that no longer exist elsewhere. Silence is also a kind of data. Jupiter's distant influence is written into Mars not as a scar, but as a limit, a boundary beyond which growth could not continue. The connection is subtle, but unmistakable when viewed over long timescales. By understanding why Mars is small, we gain insight into how planetary systems distribute opportunity. Not evenly, not fairly, but according to position, mass, and timing. Mars stands today as a reminder that in the solar system, size is not a measure of worth, and limitation is not a sign of error. It is often the natural outcome of forces acting patiently from far away, and sometimes what a world never became tells us more than what it briefly was. The region between Mars and Jupiter does not stand at the center of the solar system's story. It never did. Its role is quieter, and in many ways more subtle. The asteroid belt functions as a slow buffer, a region that redistributes material, moderates motion, and absorbs change over long spans of time. It does not direct events. It shapes how events unfold. In the early solar system, matter did not move cleanly from one place to another. Dust and fragments followed curved paths, influenced by gravity from many directions at once. The asteroid belt became a zone where some of that movement slowed down, where trajectories were altered rather than accelerated. This slowing mattered. When material moves too quickly, systems become unstable. Collisions grow violent. Paths cross too often. The belt acted as a region where motion could be redirected, dispersed, or delayed. Not stopped entirely, but softened. In doing so, it reduced the intensity of interactions between the inner and outer solar system. Space rarely gives us simple answers. The belt did not block material outright, and it did not deliver it efficiently either. Instead, it spread interactions over time. Some objects were sent inward, others outward, many never reaching either destination. This gradual redistribution reduced extremes. It did not eliminate chaos, but it slowed it. Numbers whisper more than they speak. When scientists track how material migrates through planetary systems, timing often proves as important as quantity. A small amount of matter delivered steadily can matter more than a large amount delivered suddenly. The asteroid belt helped regulate this timing. It turned sharp flows into long, uneven trickles. This has implications for the inner planets, including Earth. Water-rich and carbon-bearing objects did not arrive all at once. They arrived intermittently, over extended periods. This gradual delivery allowed surfaces and atmospheres to adjust rather than be overwhelmed. The belt did not provide Earth with everything it needed. It was never a supplier in the usual sense, but it shaped how materials moved through the system, influencing when and how certain ingredients could arrive. Silence is also a kind of data. From a distance, the asteroid belt appears uneventful. Objects follow stable orbits. The region looks calm. But this calm reflects a filtering process that has been operating for billions of years. Only certain paths persist. Only certain exchanges remain possible. For humans, this kind of role is familiar. Many systems rely not on central control, but on intermediate layers that absorb shocks and slow transitions. These layers rarely attract attention. They are noticed only when they fail. The asteroid belt did not fail. It endured. By remaining modest in mass and dispersed in structure, it avoided becoming dominant. By avoiding dominance, it avoided triggering further instability. Its value lies precisely in its restraint. This perspective helps explain why the belt is still there at all. A more massive region might have caused greater disruption. A more empty region might have allowed faster, harsher exchanges. The belt occupies a middle ground that favors longevity. Silence is also a kind of data. When we look at the solar system today, we see a structure that has remained stable for an extraordinary length of time. That stability did not come from force alone. It came from balance, from regions that slowed change rather than amplified it. The asteroid belt is one of those regions. It does not command attention. It does not dominate outcomes. But by moderating movement and spreading interactions across time, it helps shape an environment where planets could settle into lasting orbits. In complex systems, the most important roles are often played away from the center, not by what pushes hardest, but by what quietly slows things down. Even now, the asteroid belt is not frozen in time. It looks calm from a distance, but change continues within it. Not as sudden events, and not as dramatic transformations. Change arrives here quietly, in small increments, spread across immense spans of time. The most common process is collision, not the kind that shatters worlds, but gentle encounters between small bodies. Pebbles strike rocks, rocks chip away at larger fragments. Each impact removes a little mass, reshaping surfaces and creating smaller pieces. Over millions of years, these tiny losses add up. Space rarely gives us simple answers. These collisions do not erase the belt. They refine it. Large bodies become slightly smaller. Small bodies become dust. Dust drifts away, pushed subtly by sunlight or guided into new paths by gravity. Nothing stops all at once. Everything continues slowly. Alongside collision is drift. Orbits are not perfectly fixed. They shift by tiny amounts as objects interact with light, heat, and gravity. Over long periods, these shifts can move fragments from one region to another. Some are nudged inward, others outward. A few leave the belt entirely, becoming visitors to other parts of the solar system. Numbers whisper more than they speak. The rate of loss is modest. Compared to the dramatic early history of the belt, today's erosion is almost imperceptible. Yet it never fully ceases. Each generation of fragments is slightly smaller than the last. Each cycle leaves less behind than before. What remains is a structure that persists not because it is unchanged, but because change is slow enough to allow stability. The belt adapts without collapsing. It loses mass without losing identity. Silence is also a kind of data. This long-term evolution tells us something important about planetary systems. Stability does not mean stillness. It means balance maintained through continuous adjustment. The asteroid belt survives because it sheds energy and material gradually, avoiding the buildup that could trigger disruption. For humans, this pattern is familiar. Many enduring systems do not last because they are rigid, but because they yield just enough. They release pressure over time. They wear down instead of breaking. The asteroid belt embodies this principle. It has been losing material for billions of years, yet it remains recognizable. Its role has not vanished. It has simply softened at the edges. From Earth, we sometimes imagine cosmic structures as permanent. But permanence in space is relative. What lasts is what changes at the right pace. Too fast and it disappears. Too slow and it becomes unstable. The belt occupies a narrow middle ground. Even now, its future is not static. Given enough time, it will continue to thin. Objects will continue to migrate. Some fragments will find their way to new environments. Others will be lost entirely. The process has no clear endpoint, only direction. And yet, For all this gradual loss, the belt remains part of the solar system's architecture. It still separates regions. It still moderates motion. It still carries memory. Silence is also a kind of data. In the long view, the asteroid belt teaches a quiet lesson. Not all endings arrive with closure. Some arrive as slow transitions that never fully complete. What remains is not a remnant of violence, but a record of endurance. A structure can be fading and still matter. It can be changing and still persist. And sometimes, the most lasting stories are written not in moments of creation or destruction, but in the patient act of continuing on. Across the vast distances of the solar system, influence does not always arrive through contact. Jupiter shapes its surroundings without ever reaching out. Its gravity works at a distance, steady and patient, defining limits rather than delivering force. Mars responds to those limits without awareness. It grows as far as conditions allow, then settles into what remains possible. Mars does not resist. It adapts. Its size and history reflect an environment shaped long before its surface became familiar. Between them lies a region that rarely draws attention. The asteroid belt is not dramatic. It does not dominate the sky. It does not announce its presence. Yet it plays a role that neither planet could fulfill on its own. The belt absorbs change. It redistributes material. It slows interactions that might otherwise become disruptive. It exists not as a destination, but as a condition. Space rarely gives us simple answers. What makes this region remarkable is not what it became, but what it prevented. It never assembled into a planet, yet by remaining dispersed, it helped shape the architecture of the solar system. It influenced how mass moved, how growth ended, and how stability emerged. Numbers whisper more than they speak. For humans, this pattern feels quietly familiar. Some influences in our lives are never obvious. They do not act directly. They do not draw attention. But by setting boundaries and shaping environments, they guide outcomes over time. Silence is also a kind of data. The story of Jupiter and Mars is often told as a contrast between excess and limitation. But that contrast only makes sense when we notice what lies between them. A region that does not need to become a world in order to matter. Between two very different planets, there exists a space that never claimed a final form. And yet, by remaining unfinished, it helped determine the fate of both. In the solar system, as in many complex systems, the most decisive roles are sometimes played not by the largest bodies or the most active ones, but by the quiet structures that hold everything else in balance. And it is often in what lies between that the deepest order reveals itself.